the attendance link, go ahead and do that now. We're going to get started. So week 6, making parts machinable. This is pretty related to last week. So hopefully you remember what we did last week, but we'll do some review along the way. We're going to be going over a few different things. So we're going to start with making parts more machinable, but we're also going to cover some different topics: design reviews, drawing sheets, and assemblies. So we'll start with machining stuff and we'll end with CAD stuff. So these next slides are just things that you're going to ask yourself as you design a part. So what material are you going to make it out of? Aluminum, steel, if you're going to 3D print it, what kind of 3D printed material, stuff like that. How accurate does your part have to be? Does it just have to have clearance holes, or are you going to use like threads where it needs to have a specific tolerance? Or can it just be like a really rough prototype kind of thing? Simple versus complex, kind of the same thing. Does it have to be just like a fast, crank it out and make sure things fit? Or does it have to have a very specific shape and something like that in order to work? And how are you going to machine your part? And does that method allow you to achieve what you answered above? And so we're going to be talking about this kind of question today. But last week we've learned what the different capabilities of our machines are. And so sometimes you might get to the end of a part and you realize that there's actually no way to physically construct it out of what we have. Like maybe you wanted a certain shape of bent metal, but you realize that the bends don't work in the way you want them to. And so it's just something you have to consider before you start so that you don't have to go back and fix everything again. So as I mentioned before, tolerance. This is important. We talked about this a lot last week. Even though machines are more accurate than trying to do things by hand all the time, machines do have their own errors. So if you wanted to make an axle fit into a hole, you can't just have them the same diameter, because the tolerance will mean that they won't actually fit. And if you want things to move together, like if you want something to rotate or revolve around a shaft, then you'll want to make sure that that tolerance is a little bit greater so that it has that ability to rotate. You can't make anything 100% accurate. What you put in CAD, it's impossible to get it out. You can get really close, but no matter what you do or what you use, you won't be able to get 100% accuracy. And that's okay, because we just have to do as much as we can to make sure it's as accurate as possible. And generally, the more reliant the machine is on human work, the more inaccurate it'll be. So if I'm using a hand-powered mill, it's not going to be as accurate as a CNC. And actually, we're going to talk about that in the next slide. Hand-operated mills are great because they're much easier to use and they're way faster. However, that also means they're prone to errors. So because it's all dependent on the person using it. So for those of you who haven't used the mill, it's like the top is like a drill press where you just bring it up and down, but the base moves. And so you have to like rotate cranks in order to move the part where it needs to be. And there's a little readout that says all the measurements of how far you move things. And so even if you're like zoomed in on those numbers and trying to make sure that everything is as accurate as possible, there's going to be some error. And that's just something you have to accept. And so you have to combine a desire for efficiency, but also accuracy. And so there's a line that you just have to find. CNC mills, they're more accurate, but they're way harder to use, and because of that, it needs a lot more training. Mills, as a rule, just can't cut straight angles. So like if you want a corner to be exact at 90-90, it's not going to happen. You're going to have to either fillet it or do something that's, I think, on the next slide. So rounded corners should have an equal or larger radius to that of the end mill. So if the end mill itself has a radius of, say, I don't know, 2 millimeters. I'm just pulling this out of nowhere. The radius can't have or the fillet can't have a radius of 1 millimeter because the end mill won't be able to do that operation. If you think about it, it makes sense. And curves different from the radius of the end mill are unlikely to be perfectly smooth. So if you make just a 90-degree path with the mill, because the mill is spinning and it's circular, if you make just the 90-degree path, then it's going to make a fillet automatically with that radius. But if you try to make one more manually, it's going to be pretty difficult to create perfectly smooth. So something else you have to consider when you're milling a part, or when you're planning on milling a part, is how are you actually going to hold it? And usually we just have vices built on the mills. We can also use V blocks if the bottom of your part has an angle to it, or angle plates. Anyway, is just useful to hold it securely in place. And then this next part, this part is really important to reduce the number of faces that have to be machined on. So like I said, the drill or the end mill has to come straight down onto your part. That means that only the face that is up you can operate on. And every time you put your part into the base, you have to zero out a point to measure from. So you have that digital readout, you have to zero a point, and that takes effort and it takes time. And the less you have to do it, the better. And so if you keep having to change faces to put like different holes or features on your part, it can be kind of a hassle to keep having to re-zero. So try to keep as many features on just one face as possible, or as few faces as possible. So this is what I was referring to as things you can do and things you can't do with milling. And I'm not going to go through all of these, but I wanted to point out square corners. So like this would have been a 90-degree, except because the end mill is round and it rotates, it has this really awkward like circle. Or you can just have a filleted corner. Some things you can't do: 3D surfaces, undercuts, that makes sense. Text. Text would be really hard if you wanted to deboss it, but it's impossible to emboss it like in this picture where it's raised. Unless you somehow face the entire face. Anyway, doesn't make sense. Yeah, this is just a good guide, but as you use the machine, you'll learn its capabilities and what it can do. Now we'll move on to the lathe. Again, we talked about this last week, but the lathe works by spinning and cutting that spinning edge. So things have to be radially symmetric. So the cross section has to be a circular. And it says reserve circular areas for grips to hold on. So when you think about the lathe, it has to hold something in order to rotate that piece. And you want to make sure there's a nice balance between where the part is held versus where the part is being machined on. Because if they're too far, then if you think about your physics with like moment and stuff, having a long moment arm would make the part more likely to break, or for things just to not go that well. And so the rule of thumb here, we say 150 millimeters, but that's not a hard rule. Again, it's more based on just experience. As you get your eyes and hands on the machine, that you'll learn what it's capable of. And so I love this slide because I'm trying to imagine someone designing something like this and then trying to fit it into a lathe to create. This doesn't work because if this rotates, it's not going to have a circular cross section. It's going to probably just break before anything else happens. And then this has 14 sides, which is a tetradecagon. I looked that up before. I didn't actually know that offhand. It's a tetradecagon, and if you tried to stick this in the mill, you just end up with a circle, and you wouldn't get these straight edges. And now we're gonna the last machine I think we're gonna be talking about is the 3D printer. So we didn't talk about this much last week, but we've got you have to keep in mind what's the base of your 3D printer? So 3D printers work by putting just layers of material and moving the bed down as it keeps printing on top, which means that the base is super important to establish. A good rule of thumb is lying it on its long edge so it has as much surface area on the base as possible. However, we also want to reduce the amount of overhang because as it's laying on top, if it's trying to lay on top on material that doesn't exist, it has to create support structure in order to do that. And I'll talk about that in just a second. First, we're going to talk about wall thickness. It can be shown that wall thickness is way more important than just infill. So if the wall of your part is at least 1 millimeter, then it should be strong enough to withstand certain forces. I mean, if you make it thicker, then it can withstand more. It's just a rule of thumb. So depending on what you think, what kind of stresses you think your part's going to be put under, that will determine the thickness of the wall. Keep your level of detail above the minimum feature size of the 3D printer. So what that means is the 3D printer can get to a pretty high degree of detail. So like resin printers at the Invention Studio can get into the microns. It's kind of wild. We don't want to push the limits of your printer. Usually we use it for like rapid prototyping or just kind of simple things. So just try to keep things basic and large enough that it's easy for the 3D printer to read. Now back to support. So support structure is, like I said, when we have overhang that doesn't actually have any material below it to print on top of. And so support structure is kind of like scaffolding. The slicer program, when you put in the file, what it does is it just automatically programs in any support structure that's necessary. And so that just takes more time and it takes more material in order to create that support. And so we want to reduce it as much as possible by either reducing the amount of overhang by changing the base or just changing the part, or we can round overhang edges, because I think support only goes onto flat parts of the overhang. In other terms of reducing volume, you can use the shell commands in order to hollow out your pieces, or just if there's a simpler way to make your part that reduces volume, that's best practice. And when it says think about how support can be cleared, especially for holes, if you have a hole that is vertical on the printer, when it tries to create the shape around it, it sometimes has to fill it in with support. So it's best to have holes like flat on the bed so it can easily just work around it. So just keep these things in mind with 3D printers. So bad parts for 3D printing. Sphere, that's an easy one. It's really hard for support. It doesn't have a very good base because there's no flat part to stick onto the bed. But this rectangular prism here, you may be wondering, why is this a bad part? Well, any part that you could create like this would be way easier, cheaper, faster to make out of like wood or maybe metal if it's small enough, or if your stock is big enough. There's really no reason to 3D print just a basic cube. And if you try to print a basic cube like in the Invention Studio, they're going to get mad at you because it's just kind of a waste of resources and time. And there are better ways to do it. So that's that for machining. If you have any questions on like how to make parts better for machining, now's a good time. Tomas is ready to look at the chat. But I'm going to move on to design reviews. So this is going to be just a really quick introduction, but a design review is kind of an intermediate step in your design process. So you created your design, you have the CAD ready to go, and you're ready to print out measurements so that you can start machining. But the idea is we want to present our designs in front of a bigger audience so we have more eyes and get more opinions. And so we can potentially improve our design. And so we want to include the following. So we want to have a purpose. We're going to be presenting probably in front of your mechanical team, or mechanical subteam, I mean. In some cases, you'll have other teams, mechanical subteams coming in. Or if you have like a part that's related to electrical, you might have electrical coming in to make sure that things will work the way that you think they will. So you want to include the purpose because not everyone is tracking on what you're doing. Design constraints. What are the things that you have to make sure you have to watch out for as you were going in? What materials are you using? What sizes are the things you're going to be using? You want to cover all your bases. If you're going to be ready to machine stuff, you have to be ready to say, how are you going to machine it? And then CAD. You want to have your CAD ready to go. So what's going to happen is when you finish your presentation, they're going to ask to look at your CAD, and you can just move things around so that they can see things that they want to ask questions about. And if you have parts that you want to purchase or parts that you want to machine, those are important to stick out. So purchases, you want to have links, specs ready. You want to say why we're purchasing stuff instead of just machining it or pulling something out of the shop. Or if we have parts to machine, why are we not just buying it? And how are you going to do it? And then finally, potential issues that you foresee. It can help clear some questions or get opinions from people who are like, oh, if you run into this issue, this is what you can do in order to resolve it. So design reviews are really great ways to make sure that what we're doing is actually going to work. And if it's not going to work, it's a good way to get those improvements. I had a design review like 2 weeks ago, and I got a lot of good comments on things that I need to change and fix in order for it to work. And what's best to keep in mind is you don't need to take these things personally. Any improvements that people suggest or criticisms that they'll have of your design, it's just so that it's as best as possible. So you have to be ready for either you to take notes or have someone else in the audience taking notes so that you can have these things written down. So yeah, if you have any questions about design reviews, the best person to ask is your sub-team lead, your mechanical sub-team lead, because I think every team does it just a little bit differently. But yeah, I'm going to be moving on now to drawings. So if you have any questions, now's probably a good time. So drawing sheets are, we're not going to be doing these in the CAD guides until next week. So if you're not quite following, or if you want to get practice with this, just wait till next week and you'll be able to do that. But just as a quick overview, drawing sheets are used so that we can express measurements and get rid of ambiguity when we're trying to describe how a part is made. So this is helpful when machining, both for us and if we're exporting it, then we have to send them a drawing sheet. You're not going to just like carry your laptop into the shop or like memorize all your measurements because that's not great practice. So when we create a drawing, then we could just print it out and carry that paper around with us. So to create a new drawing, it's just like creating a new part. So you have assembly, drawing, and part. We're not going to get to presentation in this mechanical training, but it's kind of neat. But anyway, you can just click drawing, DWG, and from there, yeah, you'll get practice next week on how to create things. We use size A2. It's just letter paper, picture paper. And so these are kind of bad examples, but these are examples of what a drawing sheet would look like. As you can see, stuff has dimensions. This plus minus is like a tolerance. You can see like this is the diameter symbol. Everything has a different symbol, like for holes and stuff, those have particular callouts. For people in ME 1770, we're not doing GD&T standards, so don't worry about that. We're not that fancy. You can be if you want, but it's not required. So like I said, this is kind of a bad example because not everything is dimensioned. Things are dimensioned to hidden lines, which you shouldn't do. These are just examples of section views. So like if I cut this part at a certain place, this would be the internal cross-section view, so I can dimension the inside. And then this is another section view of just like this small little button. If you take ME 1770, at some point you'll learn more about each of these things. Usually we just have to worry about a base view and then each of the multi-views. So like if you rotate your part around, like if you're clicking on the cube in Inventor to look at different sides, this is what we're looking at. And then we have an isometric view just to give an idea of what the final part is actually going to look like. And so for us, we don't use our border. This border is usually gone. You can keep this title block if you want. But these are just important for setting all of our measurements and eliminating any ambiguity when it comes to machining. Let's see here. I was going to mention something. Oh, right. So as I mentioned before with the mill, it's kind of a hassle to keep zeroing things. So what you want to do, something to keep in mind, is to set all dimensions from a base point. So if you set, for example, if I wanted to set the position of the center of the circle, which for some reason there isn't one, but let's say I had a center mark on this circle and I wanted to dimension it, I would dimension the length from the center to this corner, or to the side and the side starting at this corner. I wouldn't dimension it to this side or the top, because then I would have to either create a new 0 point, or I would have to just do some quick math with other dimensions. But we don't want to do either. We want to make the work as easy on ourselves as possible. So we want to measure everything from the same point as much as we can. And so those are the basics of drawings. We probably won't be using them this much, at least for work that's done in our shop, just because we can't use the shop as much. But it's handy to know, and it's always a good idea to show someone like your sub-team lead a drawing to make sure that it's got everything that you need. I remember I showed Ben a drawing, and he pointed out like 3 things that I missed. So it's good to just get a set of eyes on things. And next we're going to move on to assemblies. And so this is the last topic we're going to talk about. This is going to be the topic of your CAD guide. So just hang on just a little bit longer. Again, if you have any questions, the chat is always open. So we're going to talk about assemblies. This is when you are done with all the parts of your assembly, of your sub-assembly that you're working on, and you want to put it all together to see how it fits together, and make it look all pretty. And so you'll always start by fixing your first part to the origin. I personally do a bad practice of just grounding my first part. It works for me. But it's a good idea to just fix things to the origin. And we're going to be using things, or we're going to be using constraints that I'm going to be describing in the next few slides. But what using the origin does is we can use the actual origin planes when we're creating constraints, and that can be useful. So we want to constrain every degree of freedom. So as I've said, probably like the first week, there are 6 degrees of freedom. There are the 3 planes. So you've got like just basic motion, or linear motion rather. So you got forward, sideways, up and down, and then you got rotation in the same plane. So you got like a twist in this direction, a twist forward. I always somehow mess up. Oh, and twist like this. And you always want to constrain all those degrees of freedom before you move on. So if you click on a part and try to move it around, if it doesn't move around, then you're good. It's just like sketches. You want to fully define things before you move on. And then if things start erroring because constraints are conflicting, you got to stop and you got to fix it before you move on. You don't want to just like click OK and suppress conflicting features and move on, because then you'll just keep getting error message, and that's not good. So these constraints that we're going to talk about, we're not going to talk about all the options that you have, but we're going to focus on the main ones that you'll be using. Mate is probably the most used. Insert maybe is the second most used. Angle and tangent are pretty well used, and I personally don't use symmetry, but we'll get into it. Mates. So if you want to focus in on my screen, like my camera screen, I'm going to be using just like this phone and calculator as an example. So mate is when you take two surfaces, so let's say just the backs of both of these, and I'm slapping them together, and that's a mate. They can still move in the plane. Oh, you can't see me? Oh no. Am I gonna have to just stop sharing my screen? Okay.
I see you on my end, which is a little weird, but
that's fine. Now that I'm talking, if I have my two, the backs of my screen, of my phone and calculator, and I click mate, they're just gonna smack together. And they can still move on the same plane with respect to each other, but I can't move it out. So like sometimes you'll click and drag things and it looks like it's moving out, but when you rotate it, you'll find that they're actually like super far apart and still on the same plane. And you can also create a flush mate. And so what that does is they're still on the same plane, except it's just flipped. So they can move on the same plane with respect to each other, but they can't move away. And you can always create offsets. So if you say, well, I don't want these directly on top of each other, I want them an inch apart, you can do that. So let's go back over here. The angle. Pretty self-explanatory. You set an angle between things, and that's just what they're set to. Usually you'll see that there are different solutions. These are called solutions. And the left one is highlighted blue. Usually we stick to this one just because it's simplest. However, you can, the default is this third one, which I think you need to click on a surface perpendicular to your angle. But just stick to the left one and it'll do what you want it to do. Tangent. Oh, I forgot to mention for mate. There's one more thing about mate. I'll go back to my screen. Let's see here. So mates can also happen axially. So if I have this marker and this pencil, and I want them to be on the same axis, that is also a mate I can create. And so they can move along this axis, but they can't move away from it in any direction. And they can't rotate away from it. So axis mates are pretty well used. And then for tangent constraints, if I wanted to take a circular surface or a cylindrical surface, and I wanted to make it tangent to a flat surface, you can do that. And it can rotate along that flat surface, but it can't come off of it. So those are used as well. And then my favorite, here I'll share so you can see it for a minute. We got inserts. Inserts are used a ton in RoboJackets because we've got bolts that we put in all the time. And so you're downloading bolts from McMaster. We don't ever want to actually model these ourselves because that's too much work. And these models are free online. And you'll be able to see how to download them in the CAD guide. We use insert all the time because if you want to make an axial mate between the bolts and the hole, and then you want to make a face mate between like the bottom of the bolt's head and the top of your surface, that's just two constraints when you could use insert and turn it into one constraint, which is really great. It makes things faster, it makes things easier when you're trying to troubleshoot through the constraints. You don't have to scroll through as many. So to give you an example of what I mean, I'll go back to my screen here. So if I have this marker cap and I wanted to put it on this pen, then I would usually have to, if I wanted to just use mates, I would axial mate so it can move on and off, and then face mate so it actually goes on. But an insert would just do it all at the same time. So I'd click the bottom of my cap and then the place where it stops, and it would just immediately hook on, and it's amazing. So insert constraints are your best friend. So we'll go back here. And then symmetry. Again, like angle, it's pretty self-explanatory. I've personally never used it. But if you have a plan, then you can set two parts to be symmetrical or positioned symmetrically. Personally, I'd rather just use, well, actually, it's like insert where it can do a bunch of things at the same time. So if I wanted to do an offset mate and like an angle constraint, then it would just do both of those at the same time. And so symmetry can be useful. And then finally, we're going to get into kind of an advanced one. Movement constraints are like if you want two gears to move with a certain ratio. And this would be like if you want to get a proof of concepts that like your part is actually going to move the way you want it to, or if it moves the way you want it to, that's actually physically possible. You can set things to rotate with respect to each other. Or like this, there's another type here where you can see this circle and like a rectangle. That would be like if you had a circle moving on a straight gear or straight teeth, it would move the rectangle linearly as the circle rotates. So you can create some pretty fancy stuff, and you can change the gear ratio or the rotation ratio. And this is great for like design reviews if you want to show off your skill and also show off your design to just show how it works. But you want to make sure that everything else is already done, and you always want to save a copy file, because with advanced stuff, you never know if things are going to start breaking. And so if you have an extra save file, then you don't have to worry about it so much. So here's an example where someone has created just a one-to-one ratio between this gear and then this gear. And we hit apply and cancel. Then when you move that, it just rotates around. So it's hard to tell, but they're rotating around each other technically. But it's really neat. And then finally, this is this is a slide that Alex Field, who is our current president and used to be a trainer, he really likes this slide. I think it's pretty niche, but there's a button called Replace Component. And this is, let's say you have a fully constrained assembly and you feel like you're done, except you want to change all the screw holes to a different size. And for some reason, you're making it in a completely different part. You can use, if they have the same overall geometry, if the parts have the same overall geometry, then you can use the replace component in order to just immediately replace all those constraints that you've already made with this new part. And so it saves some time if you don't want to delete, place, constrain all the bolts you just had, stuff like that. Or if you want to replace all the, it's most important when you want to change all the screws. So you can select all, like, let's say you're using 12 bolts on a part, and they're, we'll use this example. You have 440 screws on your part. Let's say you have 12. Instead of deleting 12 and then placing 12 and then constraining 12, you can just select all of them, use a replace component, and then just select a 632 screw. And it'll immediately interpret those insert constraints that you've probably made, and it will just throw them in the assembly. So you just have to make sure that the features are going to be very similar. Otherwise, it's just going to tell you that you now have constraints that don't work anymore because parts don't exist. And you just have to start from scratch, as usual. But it's CAD, so it's not that hard. It just takes some time sometimes. But yeah, that's the basics of assemblies. So now's a good time to ask any questions as we log into Kahoot. I forgot to log into Kahoot, so this will give me a second. I'll start sharing once I am prepared. But yeah, I covered a lot of different content. So if you have questions, feel free to ask. Oh, actually, this is a good time. No, I'll push that later. This is week 6. Seven questions. It's a short one. I could have sworn I added questions to this. Oh well.
We did have a longer one last time, I think, right? With 12
We
questions.
did.
So this kind of balances it out.
Whoa. Why am I listening? Oh, there's a Halloween one. This is weird. It's just slow. Oh, we had some people leave. Tomas, did you catch the number of people we had? By chance?
No, I didn't. I'm sorry.
All right,
But it
that's all
should
good.
be marked from. Wait.
Yeah, so
We
right
should
now,
have it from like the attendance link, but that's it.
yeah, I think I can check that. So we have 11. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 2 more people. Well, there should be 2 more people. I'll give it another 30 seconds, I guess. People are
AFK3.
really thinking about their
Oh, no.
name. All right. Well, I guess we'll move on. Let's get started. Which of these parts are not good candidates for milling? All right. So, top left would be okay. Everything has rounded corners, or rounded internal corners. But the problem with this bottom left is this corner right here. You see how it's sharp and there's no internal fillet at all? That's just not something we can do in the mill.
For the bottom right one, please just use a water jet.
Yeah.
Like, please.
Yeah, if it goes all the way through, just use a water jet. All right, and we're off. True or false? Custom weights that overwrite the material weight are carried into the... Oh, wow, we didn't talk about this. Ooh. I don't know if I know the answer. I thought I changed this.
This is such a niche question. Oh my god.
Today I learned. I'm gonna write that down, that we need to change that. Give me a sec.
Although, if I had to be honest, like, I would always assume that Inventor does the dumb thing. You know what I mean?
Yeah, SolidWorks is way more intuitive than Inventor. But we'll see how it goes. Which constraint would you use if you want to make 2 surfaces parallel? Oh. Would symmetry do it? Okay, first, parallel isn't a constraint. We didn't talk about it at all. Angle, you can set the angle of two faces to be 0 or 180, which would make them parallel. That's a tough question.
Yeah, that wasn't fair.
I
I
think
mean, with
I
other
think I
CAD
gotta adjust
software
this
is,
for tomorrow.
yeah. Inventor's the only one that doesn't have parallel, if I recall, which is really annoying.
Yeah, that's a sneaky one. True or false? This part is a good candidate for lathing. All right. I hope the people who said true misclicked, because if you stuck this in a lathe, it's spinning like super fast. So you wouldn't be able to get these individual teeth. They would just come out as a disc. All right. Best way to constrain a screw in a hole. Cool. Insert. Thread tool isn't a constraint. Okay. 2 more questions. How do you determine what size screw hole you need to make for a certain size screw? I don't remember these questions.
We're sorry, guys, for this week.
I would have said orange.
Nope, not Imperial, because Imperial will label stuff from 0 to 12
Right.
underneath
So
a
if
certain
you look at the name
diameter.
of the screw, it's not going to tell you much. So if you use the hole tool, it'll do it for you. Thankfully, none of us are eyeballing it.
I mean, you can, it's just not a good way to do it.
Straight interior angles. Can the mill do it? And the mill cannot do it. Good.
Very nice.
So let's see who won. Wait, who did win? Ooh, we got Paul on top. Kirtik, I hate to say it, but the 1,000 points that I gave you for catching the mistake, and it didn't do it for you. So that's a Kahoot. Good job, everyone. Sorry there were some weird questions. Feel free to hop in tomorrow's call because there'll be better questions. Okay, so the guide. Before everyone goes, I just want to shout out for this poll. There's a suggestion last week about using drawing sheets instead of just the regular CAD guides, and I want your opinions on it. I also sent out an email, but we only got 1 response from it, so it's we want to get as much feedback as we can. Obviously, we can't just like change the CAD guides for this year, but this will be for the future. Here we go. It's like 1 question, 1 multiple choice question. So like it'll barely take a minute. You'll spend more time reading the question than you will answering it. But yeah. So the CAD guide. I would encourage everyone, even if you're familiar with CAD, to at least take a look at the last few slides that talk about downloading stuff from McMaster, because that's important no matter what team you're on or what you're doing or how much experience you have. It's good to know how to do it. So I'll just zoom through before I skim through this. Where is it? Okay, maybe it's not the last few slides. Yes, it is. So starting slide 49, if you go to mcmaster.com, then what you can do is you can just like find different screws, and then you'll be able to download the file in order to do that, in order to use it in your CAD assembly. And it's super useful. And actually, I think I might just make a short tutorial video on how to do that, because for anyone who just happens to skim through this and doesn't know how to do it, it's all good. So I'm just going to skim through the CAD guide. If you want to get going, then you can. But if not, then I'll get started. So first, you just got to download some stuff. This is labeled week 4 CAD zip. It's because I copied it from last year and they just had it week 4. Yeah, we're just going to be working through assemblies. So you're going to grab the parts that we downloaded. We get familiar with the new options that we can do. And then we just start placing parts, getting more familiar with part trees and folders and all that fun stuff. We're grounding the first part instead of mating it to the origin. And then we place some more parts. And we stick them all together with constraints. And so it shows how to do that. It's pretty easy stuff. The hardest part might just be transitioning between the slides and your assembly, because there are just a lot of different slides. And so you're going to be utilizing work planes to mate to instead of just surfaces. And then we're going to use some axial mates. This is how you know it's an axis, is because these solutions pop up. And you'll be able to zoom in and see exactly how things work. And it's very all well laid out. And now we're going to get out another assembly. And this is actually a whole new file assembly. And you'll ground the first part. You'll put the bearings in. And then you'll have to be really careful as you look at which of these shafts, which of the bearings. If you look at this slide long enough, you'll be able to figure out the shorter one goes in the bigger bearing. I remember having a hard time figuring out how all of this was put together. And then eventually you're going to put stuff together. It's just a lot of constraints with some offsets. But the issue is you're going to find is that these teeth are not properly spaced. So in order to fix that, or in order to check that, we can use a fun little tool called Analyze Interference. And what it'll do is it'll just like highlight where things are touching each other and how much is conflicting. And so it's a good way to check the physics of your parts to make sure things are fitting together how you think they are. And then in order to fix the mismesh, we're going to turn off visibility of all the parts that are that we're not working on. We're going to isolate some stuff, and this will allow us to work on parts individually. And what you're going to do is you're just going to go into this sketch and you're going to edit it and check original links to find the proper dimensions. And then you can, once you're done, you're just going to return, undo the isolation, and you'll see that things will fit together well. And then you'll stick on the top plate, and then you'll notice that you need some screws. So you go to mcmastercar.com or just mcmaster.com, either works. It'll tell you which screws to find. You're gonna click on the product description and then save a step file to save, and then you can bring it in to your CAD, and it'll come up with a dialog box saying like, "Are these the settings you want?" And you'll just say okay. You'll just keep whatever default settings there are. And then you can use the different mates in order to put them in, or you can use insert. And then just a final note, assemblies are really great, except there's a lot that can go wrong. And so there's good documentation through Inventor. There's good documentation just online in general. And we're good resources. So if you ever have trouble finding things or doing things, don't hesitate to reach out to the trainers or your mechanical train lead. or sorry, your mechanical sub-team lead, and we'll be able to help you. So if you guys have any questions, I'm going to hang on for a few minutes. Tomas, you can get going if you'd like.
All right. Cool. See you guys. Hope you enjoyed.
Have a good night.
Good night.